This is part 3 of Unit 5, Lesson 6, Optimization. In this final part of this lesson, we're going to talk a little bit about implicit relations and some of the conditions for justification. What you want to remember is that if you have endpoints, you want to think about using the extreme value theorem and check the endpoints, because it's possible that the conditions where you have a maximum or minimum could happen at one or both of the endpoints. And we'll see that in example 7. Otherwise, you also want to use along with that the first derivative test when you have an open interval or a half open interval, or if you want, you could use the second derivative test if it's easy for you to find the second derivative. But I personally don't believe that it's necessary to do that, because I think it's just making extra work for yourself. So let's go through a problem that's a little less traditional. So example 6, we have your house is situated along a straight shoreline. You row out 2 miles from the nearest point on the shoreline and then row 6 miles down the beach each day before school. I'm going to change some things here because otherwise the problem doesn't work out right. I'm going to say that you row at a rate of 3 miles per hour. And instead of walking, we're going to jog. And we're going to jog at a rate of 5 miles per hour. Okay, what is the least amount of time required to reach your house? How far from the house will you beach your kayak? Okay, so what this means is, even though the 2 miles is here, you're at your house, you pull your canoe out, you come straight out 2 miles this way, you row down the beach 6 miles to here, and then you row back to the shore this way. So that's what's happening here. So just to make the picture a little easier to visualize, we'll put the 2 miles at the far end. And if we label everything, what we're going to find is that we can call this X, and our distance from our house that we walk back or jog back is 6 minus X. So now we can use the Pythagorean theorem to find the length that we're rowing back. So that length is going to be the square root of x squared plus 4, 2 squared. Okay, so want to remember over here our rates, our rowing rate is 3 miles per hour, and our jogging rate is 5 miles per hour. Okay, so a couple other things. We want to make sure that our x values that we're looking at are constrained to be between 0 and 6. Otherwise, we're past where we either go past our house when we walk back, or we're further down the beach than we rode. The other thing we're going to use is the idea that distance equals rate times time. So that would mean that time is distance over rate. And that's where we're going to set up our equation, because we want to know the least amount of time. So that's going to be our optimization question, our equation. So our time equation is going to be our row time plus our jog time. All right, so I'm going to put some x's in here now, so I'm going to call this t of x. Our row time is going to be our row distance, which is that hypotenuse there, x squared plus 4, and we're going to divide it by our rate of rowing, which is 3. Our jog time is going to be the distance we jog, which is 6 minus x, and we're going to divide that by our rate of jogging, which is 5. So now what we can do is we can take the derivative of our time function. So here we're going to get the 1/2, we're going to get a 2x, and then in the denominator we're going to get x squared plus 4. And using the chain rule, we want to think of this part as 6/5 minus x over 5. So when we take the derivative of that, we just get negative 1/5, because that's a constant, and that's just x to the first power. Okay, cleaning this up a little bit here, the 2's will cancel, so we get, I forgot my 3 in here too. Okay, I forgot that. So we have x over 3 times the square root of x squared plus 4 minus 1/5. Now we're going to set that equal to 0 and find our critical number. So we're going to have 1/5 equals x over 3 times the square root of x squared plus 4. So cross multiplying, we get 3 times the square root of x squared plus 4 equals 5x. Squaring both sides, we're going to get 3x squared plus, oh, I'm sorry, that's going to be 9x squared because I'll be squaring the 3. 9x squared plus 36 equals 25x squared. And then finishing that up, I have 36 equals 16x squared. So 36 over 16 equals x squared, which is 9 over 4. So x is going to equal 3/2 or 1.5 miles. I don't need the negative root because you can't have negative distance. Okay, so now we have to test that point. So here's our t prime. Here's our t, and we want to make sure that we're less than 6, but of course we're going to be greater than 0. And we only have one point here, which is 1.5 or 3/2. So we can test 1 and 2, and when we put 1 in our derivative, what we find is that it's negative. So we're decreasing here, and then when we substitute 2 in our derivative, we find we get a positive number, so we're increasing, so we have a min here. And so that is going to be our absolute min. So we need to know our time when x is 1.5. So putting that back in here, we have 1.5 squared plus 4 over 3 plus 6 minus 1.5 over 5. And so t of 1.5 is approximately equal to 1.733 hours. Okay, so the least amount of time you really shouldn't abbreviate words if I'm doing it for space, is at 1.733 hours when your kayak, or is it a canoe? Does it say? Yeah, it says kayak. When your kayak is 1.5 miles since t prime of 1.5 equals 0 and t prime changes from negative to positive. Sorry, I just ran out of space. Okay, and our final example. Just in case, my favorite student found a 4-foot piece of wire left on a construction site. He is learning about optimization in calculus and wants to cut the wire to create a circle and a square. How much of the wire should be used for each shape in order to maximize the total area? Now here, we are going to have to take into account the endpoints. Like, what if we use no wire? What if we use all of it? Okay? Or if we use part of it. So we're going to be having to deal with our endpoint and the extreme value theorem. So what we're starting out with is our total area is going to equal the area of the square plus the area of the circle. Okay, what we do know is that our perimeter has to be 4 feet, because that's the piece of wire we have. So that's going to have to make up the perimeter of the square plus the perimeter. I'm going to call it the perimeter, but it's really the circumference of the circle. Okay? So substituting what I have here, so the top equation is going to be 4s, I'm sorry, this is the area equation, is going to be s squared, the area of the square, plus pi r squared, the area of the circle. So my perimeter, 4 is going to equal 4s plus 2 pi r. Okay, so now we have two variables. We want to get rid of one of them. Looking It doesn't matter which one you get rid of. I'm going to get rid of r. So I'm going to do 4 minus 4s equals 2 pi r. So r is going to equal 4 minus 4s over 2 pi, which is 2 minus 2s over pi. That's my r. So now I'm going to substitute that in my area equation. So it's going to be a of s is going to equal s squared plus pi times 2 minus 2s over pi squared. So multiplying the top out, squaring that, and simplifying my pi, I get that a of s is 4 minus 8s plus 4s squared over pi, and then I have that s squared. Okay, so making this a little easier to deal with, I'm going to factor out a pi, and then I can kind of combine like terms. So a of s is going to equal 1 over pi times 4 minus 8s plus 4s squared plus pi times s squared, because then when I distribute, the pi will go away with the s squared. So I kind of have like terms. Is 1 over pi times, so I'm going to have, this should be squared, 4 plus pi times s squared minus 8s plus 4. That's going to make it a little easier to deal with. I'm going to set that equal to 0. Oh, I got to take the derivative first. It just makes taking the derivative a little easier. So a prime of s is going to equal, I have my 1 over pi here, and then I'm going to have the 2s, and then I still have the 4 plus pi here, and then I have minus 8. Okay, so this is what I'm setting equal to 0. So I can get rid of the 1 over pi, I can divide it out. So I have 2s times 4 plus pi minus 8 equals 0. So I have 2s times 4 plus pi equals 8. So then 2s is going to equal 8 over 4 plus pi. So s is going to equal 4 over 4 plus pi when I divide by 2. So this is approximately equal to 0.56. Okay, so making a sign chart here, I am going to check my endpoints too. I'm going to check 0, I'm going to check my 0.56, and I'm also going to check by 4 as well. What I'm going to find is that I actually can't use the 4. As big as I can make it is 1. Because if you think of a square, there's all 4 sides. I'm going to need 1 inch on each side, or 1 foot on each side. So that'll be a total of 4. Because remember that my s is the side length. So the least amount of side length I can have is 0. The biggest amount I can have is 1. But I wrote that there, so don't be careless. Think about what your s is standing for. So we can only be between 0 and 1. So I'm going to use 0.25 in tests. I'm going to use like 0.6, and I'm also going to use 1. Okay? And remember, here at the endpoints, you put the value of the function in. So the area of this square right here is going to be 1. If I put 0, a of 0 is going to be 0. So let's see what happens in between. If I use 0.25 in my derivative over here, I get a negative number. Oh, I'm sorry, wait. 0.25, I get a positive number, so this is increasing. If I put 0.6 in here, I get a negative number, so it's decreasing. So I have a max here. But I've got to find out what that value is. And when I do that, I get a of 0.56 is going to be 0. Well, no, that's the derivative. So it actually comes out to be a number that's negative. So here is where my maximum is, at the end point. Okay, so the maximum area will occur when Justin uses the 4 feet for a circle only and no square. So S is equal to 0. And my reasoning can be that, whoops, this is true by the extreme value theorem, the EVT. And that's the end of this lesson, and we will go over it in class.